Hello, this video is to discuss scatter plots and correlation. Um, we want to look at two variable data here, and I've got an example where we are comparing heights of apple trees to the number of apples they produce. So I am comparing two different items here. Across the top line I have a set of data for each tree, and the bottom line I have the number of apples on each tree. So the first tree was 15.2 feet high, and it produced 120 apples, and I have data for 10 of those trees. So we're trying to see if the height of the tree affects the number of apples on the tree. So generally we'll call the first set X, which is a explanatory variable, and the second set of data Y, the response variable, since we're trying to see if there is a correlation, if the height actually affects the number of trees. And sometimes, especially for graphing, as we're going to get into, we could look at each tree as a point. So if you're familiar with XY graphs, that's how you can relate this data. Alright, so here what I've done is I've created a scatter plot, which across the bottom is my x-axis, or the height of the trees, and I rescaled this just to kind of capture the data I have here. Notice it doesn't start at 0. It starts at 15, which is about the height of my first tree. And my smallest number of apples was 110, so I started my y at 100. So anytime you make a graph, always make sure you label everything. But each one of these particular points, it represents a single tree. So the graph will help us understand if there is a relationship between them. Besides making the graph, there is a calculation that will tell you how well they relate to each other, and it's called the correlation coefficient. It's usually represented by the variable r. And down here is the formula. I know it's a scary formula, but r is a fraction. It's the number of items times, and you may recall the capital sigma symbol here from when we calculated standard deviation. That means the sum. So it's the number of items times the sum of the two variables x and y multiplied together. And then we're going to subtract the total of all the x's times the total of all the y's. That's on top. Then on the bottom we have the square root of the number of items times the sum of x squareds minus the sum of x, and then we square all those. Okay, so two very different calculations there. Then we multiply that by the same calculation of y's. So both x and y is included in this calculation because we're trying to see how well they relate to each other. The way this is set up, it will produce a fraction, which of course fractions can be turned into decimals. One thing here is r should always be between -1 and +1. So that means it could be 0, it could be 1/2, it could be -2/3. Just kind of shows the strength of the relationship. As a quick note, the closer it is to -1 and 1, the outside parameters, that means the stronger the correlation, and the closer it is to 0, there's less correlation, as we'll see on graphs in a moment. So I made a table here to kind of show you how you would calculate this, and hopefully if you have to calculate one by hand, it won't have as many data points. But I have my x and y columns, and at the bottom I have the total. I made a column for multiplying x and y. I made a column for x squared and a column for y squared. So I have all that data, and I have all the totals down here. And I also took all those totals and listed them across the bottom so that you could see them. So all the x's add up to be 180, all the y's add up to be 1620. If I multiply x and y and add them all together, 29,818. All the y squares, 275,350. Here's the first calculation. I add up all the x's and square them, so that's the square of the 180. The second one here, I add up all the y's and square them, that's the square of the 1620. Over here, the total for the x squared column, 30 3,286. Okay, so I'll need all those for the R formula. Okay, so I carry that over and I try to plug it in. And this is a place where you really need to work with your calculator to make sure you feel confident and understand how the formula works. So I plugged in all my values. Everything is used to just kind of help you follow along, but eventually the correlation coefficient here is 0.8467. Okay, that's fairly close to 1. Of course, we're dealing with small numbers, so how close to 1 it is might kind of throw you off, but let's keep going. So we just talked a little bit about the fact that it needs to be between -1 and 1, and we're showing how closely those two are related. So here's some graphs to kind of give you a good idea. So first of all, I said it needs to be between -1 and 1. Over here in the first column, I have two graphs. Notice that as you look at this, the graphs are going down. That would be a negative number for our negative correlation. That means as x goes up, as we follow from left to right, that the y's go down. Okay. Same thing here. In the middle, I have some that would be kind of close to 0. You may notice that they're all over the place. So over here, you could kind of, in the first column, you can see a trend going down, but here you can't really make a trend out of this. Okay, so that correlation coefficient of 0 means they're not really related at all. You can't make much of a prediction from one onto the other. The last column is a positive, so these are kind of close to a +1 because they're both going up. As x increases from left to right, y increases. All right, so a little practice with that. Our 0.8467, if we go back, was definitely a positive number, and from the graph you can see as we go from left to right, the y's go up. So eventually we'll make a trend line in 4.2 to show how the data does trend here. Okay, thank you.